So this pre-lecture video is going to discuss concepts involving work and energy. Specifically, we'll focus on talking about kinetic energy and develop a work energy theorem. So first, I'm going to say briefly something about energy, and we'll come back to this in class and later in these chapters. Chapters 6 and 7 both deal with work and energy. Now, energy actually has a very, what seems like vague definition, which is that energy is the capacity to make something happen, which is uncharacteristically vague for a physics definition. And the reason is that there's very many different types of energy, and every type of energy has a very specific definition. So the general definition of energy has to be vague enough in order to include all of these different types. Energy of motion, for example, something moving fast has the capacity to crash into something and cause damage. A ball that's held at some height has the capacity to eventually fall to the ground and hit something below it. A battery has the capacity to make a light bulb turn on. That's going to be a chemical potential energy. So this vague definition is actually a good working definition for conceptual understanding of what energy is. Now, work, on the other hand, has a very specific definition. And what we'll see is that you're going to have to separate out the physics definition of work from your normal everyday definition of work. So think of this essentially as a new word and a new definition. So the work, which we'll call W, and the units of work are going to be what's called a joule, which is equal to capital J, and that's equal to a Newton times a meter. Now, work is a method by which energy is transferred. So it's a method of energy transfer. Energy can be transferred between objects, and then in that case, one object will lose energy, another object will gain energy. And energy can also change types. You can change from energy of motion to a stored energy, or a stored energy into an energy of motion, for example, or different types of stored energies. And we'll get to that when we deal with conservation of energy. Okay, so a good analogy between using the terms energy and work is to talking about spending and money. So we would say that work is to energy as spending is to money. You would talk about spending $5. The $5 is the money, and the spending is the way in which it was transferred. So you would then talk about having work done on a system, and then that implies that you've transferred energy. So if you do 5 joules of work, you've transferred 5 joules of energy. So let's write that down. So if we have 5 joules of work done on a system, then 5 joules of energy is transferred to the system. And then if you have negative 5 joules of work, because negative work is possible, then what that means is that 5 joules of energy is transferred away from the system. So the system then would lose energy if negative work is done. So just like spending and money, you would spend $5, in which case the quantity of money is $5. Work and energy have the same unit. So this unit of the joule is the same for both. Okay, so work is a method of energy transfer, And specifically, it's going to be the transfer of energy when a force is applied. So we will see later in your general physics sequence that when you start talking about, say, thermodynamics, you can transfer energy via heat, which is another energy transfer process. A change in temperature can create an energy transfer process. But work refers to the type of energy transfer that happens when there's a force that's applied. So we can quantify this relationship between work and force. And I'm going to write down the general equation for finding work, which is that the work net is equal to what's called a path integral of the net force that acts on an object dotted into the displacement vector dl. The work then by just one force would be a similar expression, this path integral, which I'll conceptually describe in a second, times the force dotted into the displacement dl. So you can either talk about your net force or an individual force. Now, we won't often be working with this very general formula, which involves a path integral of this scalar product, just because the prerequisites for this class mathematically aren't advanced enough to deal with those. But we can conceptually understand this expression, and then we'll see how we can apply it to simpler cases. So to understand this, first, one important thing about work is this scalar product. So recall the scalar product. If you haven't yet watched the video on Canvas about the scalar product, I suggest that you do that at this point. Okay, so A dotted into B gave us the magnitude of A times the magnitude of B times the cosine of the angle between them. So that's the angle between A and B. And so conceptually, what that meant is that if we have some vector B and some vector A, and there's some angle between them, that B cosine phi is simply the portion, the component of vector B that lies parallel or anti-parallel to vector A. So what that implies then is that it's only the component, so F dot dl, having this dot product, means that it's only the component of the force that is along the displacement dl that contributes to the work. So if the force is perpendicular to the displacement, then you're going to have zero work done. If the force is going to be parallel to the displacement in the same direction, then you would have positive work done. If the force is opposite the displacement, anti-parallel, then you would have negative work done, right? And that comes from looking at this relationship there. So if we have here, for the scalar product, if A is perpendicular to B, then A dot B equals 0. And if A is parallel to B, then A dot B is equal to a positive, and it's just equal to A times B. And if A is anti-parallel to B, then A dot B is going to be equal to negative AB. So in this case, we're talking about the small interval of displacement that has been then divided up, so that this path integral talks about perhaps some curved path where you would maybe have at some given moment some small displacement dl. So your force then would then be integrated over this whole length of the path. So if it's a multi-dimensional path, say 2 dimensions, then this would be a 2-dimensional integral over x and y. And you can see then why having only a prerequisite of Calculus 1 is not sufficient yet to be able to do some of those more complex integrals. What we can do is talk about some special cases for this equation. So let's talk about 2 special cases that will apply. The first one is, let's say that the particle moves only in 1 dimension. So now we're talking about a path that's a straight line. So let's say it moves only in 1 dimension, which we'll just call x for the direction. And so all that's going to matter is the force that's along x. So all that matters for the work done is going to be F sub x. And again, that's going to be because F sub y is perpendicular to the displacement. So it does no work. So we can then say that this dl is simply dx. And so then we can write F dot dl as equaling F sub x dx, the component of the force along x times dx. So in this case, the work done by F would be the integral over from the initial position to the final position, xi to xf, of F sub x dx, where if you have some angle that the force makes with the x-axis, say f cosine phi, then this would be the component of f along the x direction. So what we want to recall for this is that the integral corresponds to the area under a curve. So that if we're given a graph of the force F sub x versus x, then what that tells us here is that the area is equal to the work. Alright, so this is now a more manageable integral, and it has this conceptual application of area that can be very useful and easy to solve mathematically. All right, the second special case, if we look at our general equation again, one we assumed a constant force, one we assumed a force along just one direction, and now what we can do is assume a constant force. So the second special case is that of a constant force. So let's say that there's a constant force, which we'll call F, and there's a displacement vector for the entire length of S. And now we don't have to deal with an integral because the force is constant. So the integral, if the force gets pulled out of the integral, for this path integral along the whole length of a path, will just be equal to our displacement. Oh, sorry, not ds, just s. Okay, so if we have a constant force and a displacement s, then the equation for work becomes even more simple. And it's simply going to be equal to the force F dotted into the displacement S. which again, remember from our definition of the dot product, is going to be the magnitude of F times the magnitude of S times the cosine of the angle between them. So you can think of this as the force multiplied by the component of the displacement along the force, but you can also write this as the displacement, the magnitude of the displacement, times the component of the force along the displacement. So that's more common to think of it as the component of the force along the displacement. And then remember that this angle phi is the angle between them. So again, if the force is perpendicular to the displacement, then we're going to have no work done by that force. And if the force is going to be parallel to S, then we're going to have that the work is just equal to F times S. And then lastly, if the displacement equals 0, then there's no work done. So that's not always obvious. If you push a box one direction and then you push the box back to where it was, that then because the displacement is 0, there would be no work done in this situation. And we'll see how that applies to various situations in a few examples. Now, before we do the examples, we're going to talk about what's called the work energy theorem. Okay, so far we've discussed the definition of work, and we've seen that how much work done has to do with energy transfer. And now we're going to define a specific type of energy, which is called kinetic energy, which, as I've mentioned, is the energy of motion. So something moving has this kinetic energy, and the kinetic energy is equal to 1/2 times the mass of the object times the speed squared. And like all energies, it's a scalar quantity. This expression, you can see section 6.2 for the derivation of it. Now, if this is our kinetic energy, which is our energy of motion, then it's going to depend on the mass. The heavier object would have more energy moving at some given speed. And it depends on the speed squared. So if you double your speed, it's actually 4 times the amount of energy. Alright, so that is something that kind of matches our intuition when we think about motion and kind of our idea of energy contained in that motion. And now what we're going to see is how that relates to the work done. So we're going to now write down the work energy theorem, which is that the work done by a net force on an object equals the change in the kinetic energy. So the work done by the net force acting on an object. So you're going to have to use some of your skills from the previous chapter where we learned to identify forces and come up with the net force acting on an object. So the work done by a net force acting on an object is actually going to equal the change in kinetic energy. Mathematically, we write that down as the total work, which is, remember, the work done by the net force, is going to be equal to the change in kinetic energy during which time that work was done. So K2 minus K1, which is commonly called delta K. And this is our work energy theorem. Note that you can have negative work. So if you have negative net work, then that means the object is slowing down. And this makes perfect sense when we actually relate this back to our other definitions when from discussing kinematics. So when would you get negative net work? You get negative net work, this is going to happen if the net force, right, which remember the net force is related to the acceleration, is opposite the displacement. So if your net force is opposite your displacement, that tells us if your net force is opposite the displacement, the acceleration is opposite the displacement. And remember that the direction of motion is the velocity. So this basically implies then that your acceleration is opposite your velocity, which means that your object should be slowing down. And this is then consistent with that. So the opposite of the displacement, if the net force is opposite the displacement, then we remember that displacement is related then to your direction of motion, which comes from the velocity. So that's consistent with our previous understanding from kinematics. Okay, as a first example, let's talk about the force that acts on an object moving in one direction. So let's say you're told the object starts at the origin and it's moving initially with some speed v naught x. Say it moves along the x-axis subject to the force shown. What is the work done by the force F sub x on the particle as it's moved from 0 to 6 meters? So to do this, whenever you have this graphical representation of a problem, you need to remember that you can use the simplification of a particle moving only in one direction, in which case the work done by the force F is going to be equal to the integral from x initial to x final, in this case 0 to 6, of F sub x dx, which means that this is equal to the area under the F sub x curve. So I've already marked this off here, this area portion, and I've marked for each segment what that work would be. So here, for example, 1 Newton to 1 meter corresponds to 1 joule, because that's the area of this segment. From 1 to 2, the displacement is 1, the force is -2, that's going to correspond to -2 joules of work. So in this portion, then, energy is taken away from the system. That's what a negative energy or negative work corresponds to. So here we have positive 4 joules. That comes from 2 times 2, and again here energy would be added to the system. And then here energy is taken away in both of these situations. So what you can do is then say that the total area is equal to -1 joule. 1 plus 1 is 5, and then -2, -1, and -3, those all sum to -1 joule. So that means that the object lost 1 joule of energy if this is the only force acting on it. If it's the only force acting on it, so if this F sub x is equal to the net force on the object, then we know that it lost 1 joule of kinetic energy. And we would then be able to make some determination about its final speed if we had more information about its mass. Okay, as a second and last example, let's say that we have a case of a person that is just carrying a box. They're exerting a force just holding a box up. Let's make them happy. Okay, and then they're walking at a constant speed across a level road or level ground. They're still happy. And let's say that their displacement then is delta S. So the box, say, has a weight of m times g. And there are 2 parts to this question. The first part is, what is the work done by the person as they carry the box a distance delta s with a constant speed v. So they are walking at a constant speed. They're carrying the box on level ground. And the question is, what is the work done by the person? The second part to this is, what is the work done by gravity, by the force of gravity, in this same time? Okay, so to examine this, we always want to look at the forces acting on an object. Well, it's moving with a constant velocity, so there's no forces, no net force of any concern acting in the horizontal direction at all. And so we know that there's going to be the force, the normal force from the person's hand holding the box up. This is going to be the force on the box from the person. And then we also have the weight, which is mg. And we know from our previous chapter that the normal force would equal mg in this situation because it's not accelerating in the vertical direction. Now, what we also know, right, is that our displacement, delta s, is perpendicular to both the force on the box from the person and the force on the box from the earth. So both answers are 0. And this is going to be because the normal force is perpendicular to the displacement and the force of gravity is perpendicular to the displacement as well. And so anytime you have a perpendicular force, then you would have no work done by it. So in this case, as this person is carrying this box, it does not matter how heavy it is, they are, according to the physics definition of work, not doing any work on that box. Okay, that ends our video for today. As always, if you have any questions, please let me know.